All right. So today we originally I wanted to only just do two of the pages, but my other class insisted I keep going. So I guess I'm gonna end up doing 3 pages, and that's gonna make next Thursday a rather short recitation. But I guess we'll go and do it that way. It does also mean that like you guys can come with extra questions if you want to. But so let's talk about this kind of in a brief overview kind of way. So we first talk about things this concept of linearization and also of using differentials. So that's pretty much what the first 2 pages are all about: is linearization, differentials. Plus these 2 problems at the end that are just like recall the name of a theorem. As long as you understand what the theorem is saying conceptually, you should be able to figure out which theorem it is. And that's sort of the first half of everything. Even in the Craig's slides, he actually splits these topics into 2 sets of slides. One that is about linearization and differentials, or linear approximation and differentials, as he calls it. And then the other is pages 3 and 4, where you start talking about this minimum, maximum, local, and absolute, and what I guess you'd technically call optimization. So we'll get part of the way into that, but we're starting off with linearization and differentials. Okay. So to start with, let's write down what linearization is about. So where's my cursor? Ah, okay. Linearization, well, the main thing that you should be able to remember is the formula for it. So you center your linearization or your linear approximation at some value A. And so then with that value, you have f of A plus f prime of A times x minus A. Okay. And the picture that you should have in mind is we have our generic kind of function, and say that we're trying to center at this point A. So the idea is that if you zoom really close into that point A, the function kind of flattens out, and the way that it curves flattens out as you zoom closer and closer in. And so the closer and closer you get into the closer you get to A, the better it can be approximated by just a straight line. So that's why we have this idea of linearization, linear approximation. For values very close, you can approximate it with a straight line. But yeah, this is saying that like our change in x, our little deviation from that a, should be really minuscule, like 1 in a million or something, 1 over a million or something, right? Or in our cases, it's like 0.1, but right, that's the scale that we're kind of thinking about. We're not thinking about like taking a and then going to a plus 1. That we're thinking about taking a and going plus some really small quantity. Okay, and so then let's also explain why this formula makes sense. So the way you should think about this is the x minus a is to just center it at a. So like you're focusing in on the point x is equal to a, and at that point, this f prime of a is matching up the slopes. So the derivative at a, you want your line to match up with the rate at which the function is changing. So you have this as your m for your line. And then this f of a is just scaling it so that you actually hit the line, hit that point exactly. In fact, the way that you like even closer see it is you move this f of a over to the other side, and you see that this is actually just point slope form to make it match this point here, a comma f of a. That's what linearization does. And okay, one other thing I commented was that you have actually a bunch of different possible linearizations. It would be more technically correct to specify which linearization we're talking about by saying like, oh, we're we're linearizing at the location A. And so like it would make sense to have like some kind of a subscript there to specify, because for any point we can linearize at that point. But this notation is not usually used because usually you don't have multiple linearizations. Usually you're only looking at one place. And so it kind of is clear from context where you're talking about. So we never write this value A. We never specify. Okay. All right. Yeah. Now let's go ahead and do a few problems. So this one, the information is basically just given to you. You can just have to read it and see that. So we want to work with this function s of t, but we're not given very much information about it. We're only given information about it at two pieces of data about it, this position data and this velocity data. So that tells me s of 1 and s prime of 1. Right? It tells me s of 1 is this 5 centimeters and s prime of 1 is this 2 centimeters per second. But that's precisely the information that I need to construct a linear approximation at t equals 1. Okay, so we can go ahead and do that. And then, well, the problem asks us to use the linear approximation at t is equal to 1.1. Okay, so let's go ahead and let's construct that linear approximation. So we have the s of 1, which is 5, plus s prime of 1, which is going to be 2 times times t minus 1. I'm using t just because normally you would say x, but because we are thinking of t as being some time input, t makes sense as a variable name. And we have 1 minus 1 because we're centering at 1. Okay. From here, I don't want to do any algebra to rearrange this, because it turns out that you almost always want to keep that information about where you're centered at. So don't expand this, just leave it as is, and then plug in 1.1. Okay, 1.1. And so when we plug in, we get 5 plus 2 times 1.1 minus 1. Well, that's just 0.1. And so we get 5.2. And the units for this problem are centimeters. Okay, so we can just box this guy. Right. And it might make sense to also say a little bit about like why this is doing the right thing. Okay, so the problem is actually wanting us to approximate the location of the particle, the location of the particle being given by this s. So the key thing that makes linearization work is that this s of 1.1 is approximately given by the linearization function that we computed and plugging in 1.1. So it's this approximation thing. So sometimes like it might make sense to write that down. I'm just gonna write that down. Okay, that's why this is giving us an answer. Okay. For number 2, the information is actually given to us in mathematical form, so we don't need to like convert it or anything. We can just go ahead and start writing the linearization. And then later it's asking us to use it to calculate revenue at the value 502, where we're given information at 500. So we centered at 500, we're calculating 502. And with respect to these numbers, like, yeah, that difference is kind of small. Okay, so linear approximation. This time I'm going to use p because the input is like a quantity or something. It's using p for quantities of some kind. Actually, let's give it p is a price. P is a price. Well, that's fine. All right, so yeah, the values given are 5 million, and then plus it would be the derivative here, so 40,000. And then it would be p minus where you're centered at, so 500. Okay. And so now to use the linear approximation, we would just plug in 502. And let's see what that gives us. So that'll give me 2 times the 40,000. which is going to be 5,080,000. And this is measured in dollars. Okay. And just like before, I can say something about like why this thing is getting as close to the actual thing. This linear approximation is approximating what we would get if we plugged into the revenue function 502. So this should be, this value that we got out of our linear approximation should be approximately the correct value compared with like what we would want to do, which is to plug into the revenue function. Okay. Any questions so far? No. Okay. Right. So now we start to talk about differentials. All right. So differentials are a bit weird, I guess. I definitely didn't explain it that well the other class. But so normally you're told like you've got this kind of quantity dy dx, and you're told like this is not a fraction in actual fact. You can't really like break it apart. But now here we're all of a sudden sort of breaking it apart. So something funny is going on, right? Really, this expression is saying how does dy relate to dx, like as a proportion. You're kind of thinking how does this how does y change when you change x? This is the way that the two infinitesimal quantities are related to one another. When we start to talk about things in terms of differentials, it also is a statement of that nature, but there's maybe I guess it is just really the same. Well, except that it kind of lets us plug in a bit more. It's like the way I'd like to think about it is that you're actually kind of pretending that you're doing a derivative with respect to some time, some dt, but then you're kind of just erasing that ddt at the end. So like if I take this derivative, so just treat this as like an implicit derivative, and then maybe it'll feel a bit more comfortable. So like if I just take the derivative of this equation, I'll get dy is cosine of x, but then I have to remember, oh, there's like a chain rule, which is going to give me a dx. Right. So if it feels weird to you, yeah, it gets a bit, you have to kind of get used to it. So you can kind of think of this in two ways. The first being the one I said, where it's like, oh, treat it as like an implicit derivative with respect to time, but then erase the ddt's. The other way is like, oh, just take the derivative like ordinary. You could just do a dy dx, but then you multiply the dx to the other side, which is also really a bad way of saying it because you're not supposed to treat these as fractions that you can just grab one side and. But I don't remember. I don't remember being like technically taught like exactly how you're supposed to think about it. But when you stare at this guy, at least you are told some other information than just saying like that. So this is kind of just saying like how does x and y relate? But this lets us plug in a different kind of way. This is saying like if we specify how much we change our x. So say we start at x equals 1 and then we go to x is equal to 1.03 or something. Like the 0.03 is being like our dx. If we increment by like 0.03, how will my y actually change? This kind of thing is more like I can plug numbers into this and I can get like approximate values out. Which is the whole point of like this next part, is to be able to approximate. Like, so here in part B, we would start with x equals 0 because that's a very easy value that we know how to plug into the sine function. And then the actual value we want to plug in is this 0.2. So the dx is going to be 0.2. Okay. So that's our little discrepancy. And then with this formula from part one, part A, we can figure out how will my y change, or what is my expected change in y if I go from 0 to 0.2. Okay. And so let's see, dy according to this, well, I should plug x equals 0 in. So I'm going to cosine of 0, which is 1. and then times 0.2. So I'm gonna end up with 0.2. Okay. And the thing is that that doesn't fully answer it. You have to use this as your dy, right? So we have to compare against our starting point, which is sine of 0. In this case, sine of 0 is just 0, so this is actually the value. But you should be a bit careful and say, like, for the value y is equal to, well, it don't want to say y, actually, I'm thinking. Maybe. I think maybe the saying y equals is a bit unnecessary, but sine of 0.2 is approximately sine of 0 plus the dy that we just computed. Okay, so if we didn't start at 0, but we started at, like, say, pi over 4 or something like that, then this would be a non-zero value. But you would still be able to measure out, like, how much you expect the y to change if you changed x by a certain quantity. Okay, but here, yeah, this is just 0.2, as we talked about before. Okay. Does this sort of make sense? I'm not hearing any no's, so I'll just, okay, so at least someone says yes, that's good. Yeah, right. If not, like, it takes some getting used to. Like, the real reason I want to actually say, like, you shouldn't think of it as this dt is because actually you don't have a whole continuum of time. You actually just have this one point in time, and then you're like, you have another point where you're trying to get to. So it's like it's very discrete. It's not very continuous, this kind of thing. So it's a weird thing to maybe wrap your head around if you're first looking at it, perhaps. Or maybe it's immediately obvious. I don't know. All right. Anyway, for linearization. Okay, so now the 4 is a very typical type of problem. This is the kind of problem that you can expect. Like, this looks very much like a test problem. Like, I've seen this kind of problem show up all the time on exams. So yeah, you're just given some function, you're asked to linearize, and then you're asked to use your linearization for something in particular here. So like so from A, you want to center your approximation at 16, and the reason why is because you want to approximate 15.2. 15.2 ends up being very easy to approximate. Yeah. And sometimes you're not told where to center it at, but it should kind of be clear from context, like what value to center at. Anyway, right, so let's just go ahead and write down the formula for linear approximation. So you would want to plug in 16, you'd want to take the derivative, plug in 16, and you'd want to do x minus 16. Right. So in the general formula, we had a's for all of this, but because we're centering at 16, a equals 16. Okay, now f of 16, you just take the square root, you get 4. For f prime, I need to do some scratch calculation. So the derivative is just 1 over 2 square root of x. And so then f prime of 16 is going to be 1 over 2 times 4, 1 over 8. And so then we get that. So this equation is my linear approximation, my linearization. Okay. And now we want to approximate this square root of 15. Well, we know that we want to plug in L of 15.2. Okay. And so we just go ahead and do that. And this is where, so one thing I need to mention is that you do need to be careful about signs, right? If I plug 15.2 into this, I'm not going to get 0.8, I'm going to get negative 0.8. I've seen some people make this kind of mistake on previous tests. Okay, so this negative is important. That's going to give me 4 minus 0.1, so I'm going to get 3.9 as my result. Okay, and maybe to also connect this to, like, why is this even an estimate in the first place? Well, this 15.2, this is f, well, I guess there's sort of like a one step removed kind of thing, f of 15.2, which is approximated by this L, this linearization. F is approximated by the linearization so long as the input values are close to 16. If you were to explain this to like another person, this is what you would say. Okay. Yeah, and then so C is now just like doing some real life kind of comparison, right? So we want to compare like how good is our approximation versus the actual, because we do have calculators, we can actually plug a square root in. And so, but we need to have at least these three words defined. And I'm pretty sure these words are on the slides, but I'm gonna go ahead. So I'm gonna go ahead and just write them out. So actual minus the approximation. And you take the absolute value. So that's what error is defined to be. And then relative error is equal to actual minus approximate divided by actual. And the percent error is relative error and then multiply by 100%. What that does is it converts the decimal to a percent. All right, let me now, good. Yeah, so let me now bring over a calculator. So you're going to be able to see, you're going to be able to see, like, I ran through these calculations before, so I don't need to re-enter them, but I'm just going to point them out. So let's see, where did I do them? I think, maybe it was this one. No, I think it was this one. Yeah, so the error, well, square root of 15.2 is this quantity. And then you subtract off the 3.9, which is our approximation, and we get this value. Okay, so we get, as our decimal, as our error, we get 0.00128. Okay. For relative error, we have to divide by the actual quantity. So that's typed format, it would be this. And so you end up with this guy, this decimal. Take absolute value of that. So 0.00032, and I kept writing 889. I don't like rounding, just like truncating. Okay, and then for percent error, we just take this decimal, turn it into a percent. So shift it over by 2. 0.0328889%. Okay. So you can see that there's very little discrepancy. Like our linear approximation was very close to the actual value, right? The actual value being right here. Well, yeah, so that's good, because that's the whole point of having this concept of linear approximation, is that we can, by using this kind of approximation, we can get at these values otherwise. And maybe I want to say just a little bit, like looking forward into, like, if you go on to take Calc 2, you actually start to learn a little bit about other kinds of approximation methods. So this actually falls under a whole family of kinds of approximation called like Taylor series approximation. So yeah, we can approximate with a line, but then you can also approximate with a parabola, a cubic. And that those terms all show up in the Taylor series approximation. And so this kind of linear approximation is just Taylor series approximation for like n equals 1. We're just like truncating it at the linear term. But you've got a whole family of these things. And so that kind of is maybe important for like engineers or physicists. Yeah, and there's even a whole other family of approximation that is done through like Fourier series methods. Yeah, so yeah, this kind of is a sort of starting point to this whole series of techniques, this whole theory. Yeah. All right. Now let's look back on problems. So 5, we've got more differentials that we're working with. And this time we're coding a sphere, and before you do anything, you better notice this. These units are not the same. And so to do anything, you've got to convert this 0.001 meters. Centimilli. Yeah. Okay. And so Right, we have a sphere. We may as well write the volume of the sphere formula, 4/3 pi r cubed. And so we want to estimate the volume of paint that is needed to coat the sphere, the volume of paint. So we start off with the sphere, and then we just sort of paint over it, and that's going to use up some volume of paint. So the thing to notice is that that volume of paint is going to be measured by the dV. Okay, the dV is the volume of paint. Yeah. And so all this is asking us to do is calculate dV. Well, we take this equation and we take its derivative, right? This weird kind of derivative. And so we get 4 pi r squared times dr. Okay. And now we think, how do we plug into this? Well, it tells us the radius is 1 meter. So that would be my r. And my dr is the change from the solid picture to the dotted picture in a sense. So the dr is this 0.001 meters. Okay. And that's all it really is for this problem. So in this case, while squaring 1 doesn't do anything, we have this 0.01. So I'm going to combine the 0.001 with the 4. And so we get this. And this is meters cubed, since this is a volume quantity. Okay. And so what I also did is I went ahead and did a decimal approximation. I'll show you on the calculator. I have a little bit more to show. So I did a decimal approximation. And the reason why is I wanted to actually just compare and see, like, what do you get if you just plug like volume at 1.001 and then you subtract off volume of 1, because that would be the straightforward way of calculating this without using calculus. Right. So if you did that, that ends up being this expression here, and you end up with this value here. And notice how close this value is. It's 1, 2, 3, 4. The first discrepancy is at like the 5th decimal place, if I counted right. Right. So that's a pretty close approximation. Yeah. And then like maybe you're asking me, like why is it that, if we can just plug these into a calculator, why do we bother? Well, I mean, maybe suppose you're on a construction job. You don't have a calculator on you. You're not going to be able to cube 1.001. Well, maybe you can cube 1.001, but versus this, you can easily just multiply 3.14 by 0.004 and you can get this value, at least something close to this value. So you can see that there's a bit less calculation work. You don't have to cube something complicated. So there's some reason. And also, most of calculus was invented before calculators, actually. Yeah. Anyway, good. 6 and 7. How are we on time? We're good on time. So 6 and 7. You just have to remember. You just have to know certain theorems. There's only a few theorems that we actually talk about in a Calc 1 class. So you learned about IVT, intermediate value theorem, and somewhere in the lectures from this week, you learn about mean value theorem. You also learn Rolle's theorem, but mean value theorem is just a specific or a more general version. It seems like you also learn extreme, but I'll just say that the two answers are intermediate value theorem and mean value theorem. Okay, and let's talk through why we can figure those out. So, reading this one, all right, it's saying your velocity at time, I don't know, initial time is 70, and then your final time is your velocity is 80. And the conclusion of this is that at some point you must have been going at 75 miles per hour. Well, the key thing to make this work is, like, you're talking about velocity as a function, and that function is continuous. So then every value between 70 and 80 has to be hit by some at some specific point in time. Like, you must have been traveling. There must be some time for which you're traveling at any given velocity between 70 and 80, in particular the 75. So that should really remind you of intermediate value theorem. Or IVT. Right. Let me switch my sharing back to the usual. Yeah. So, yeah, we talked about this a long time ago, but hopefully you have some recollection about it. This IVT. So yeah, that should sound familiar. 7 is a little bit different. So 7, it's saying something about average velocity and instantaneous velocity. And it's saying that if your average velocity along the trip was this amount 75, then at some point you must have been traveling at precisely 75. So there is a theorem, and there's a theorem that says this. The thing is that maybe I don't know, depending on how fast you are with watching lectures, maybe you didn't get to it yet, but it's called the mean value theorem. And so let's stare at the mean value theorem and see that what the mean value theorem is saying is precisely this statement. I'm just going to fill this mean value theorem. People don't really say MVT, I think, so I'm not going to put that abbreviation. But all right, so this is the statement that you'll get if you look at the slides. And just like with IVT, you've got like these conditions on the function f, right? These functions are saying that the function is nice, it's well behaved, therefore we can conclude this thing that we're about to conclude. So we want to make sure that the function is continuous, and we want to make sure that it's differentiable, right? This, in a sense, is to make sure that we can even define this thing in the first place. All right, so this is really where the core of the statement is, saying that the derivative at some point c is equal to this average. Okay, so you should hopefully be able to recognize this is an average and that this is an instantaneous. And I'll draw the picture that is kind of depicting like what is actually going on here. So let's say that this is A and this is B. So these are our 2 points in time for our trip. Like, so in the problem, you want to think of the y-axis as being like the velocity, right? Normally we would think of a trip, the y-axis would be distance, but here, because it's talking about velocity, we should think about this as velocity. Okay, and so you're going from A to B, and so one thing you can do is you can draw a secant line like that, and you have a slope of that secant line. That slope is this right-hand side, right? And so what this theorem is saying is that you can find some point where the tangent line of the function has the same slope. Visually, you can see that just by taking that line and shifting it up and down until you get it so that it intersects at exactly one point. And I'm going to try to draw that now. Missed a little bit. Yes, it's something like that. And the point where it intersects is around there, which would be where we call our C. So we can find some C between the A and B such that the derivative at C matches the slope, the velocity of the overall trip, right? Or in this case, oh wait, no, average velocity. Oh, okay. In this problem, this is actually what is this called? This is actually distance, right? Because you take the fraction to find the average velocity. So the slope is 75 here, the slope is 75 there. So this is saying, yeah. Okay. So hopefully that made sense. Okay. So that's mean value theorem for you. All right. Any questions so far? Just want to make sure. No questions. Okay. Then we should be able to finish this this third page, and then next Thursday will be the final page, and any questions that you guys will, I guess, have for me if you prepare questions for me. Right. So, this is still not as big as I'd like. Okay. Right. So now we're moving to information that is on the second set of slides. This thing about min and max, local min, local max, absolute min, absolute max. So the word local means look at values close to the given value. So all you need to do is compare around at that point. So in this picture, the parts that sort of stand out are here, 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 and here. And we can label these as being local mins or maxes, which we may as well do now, and then we just read it off for A and B. Okay, so this one is a local max because it's higher than all the values around it. When you like plug in values around it, you end up dropping down to here or dropping down to there. And so this is a local max. This point is a local max, but it's the kind that you're kind of more familiar with thinking about. So yeah, this is a very typical looking thing. This one is a very kind of weird looking thing. This one is a local min. And it the only difference is like it has a little kink there. It has a little change in the it doesn't change smoothly, but that doesn't actually matter for this consideration of min or max. All you care about is like the relative height of things. Okay. And then for this point here, well, if I plug into the right, I get values lower. I plug into the left, I get values lower. This is also a max. Okay. So that's how we think about this thing of local mins or maxes. And then we can just write these coordinates out. So the only thing that was a min in this case was this 2 comma -3. The other 3 points are maxes. So let's see, -2, 4, 0, 1, 4, -1. Okay. For C and D, it wants us to look at the full function and to talk about absolute min or max. So normally with absolute min or max, you're given a closed interval. That's what happens with like the later problems. But here it wants you to consider it on the entire function, the entire number line, the real number line, and wants you to say does this function have an absolute min or max on the whole number line? Well, so we have to look and see, well, is there some minimum value that it takes on for part C? And in this case, it does. And for this function, it does. It's got a minimum right there. You might also think this is, but that it doesn't, because when you try to plug in, you end up way up here. Okay, so this point is excluded. You actually need to attain the value that you're trying to look for absolute mins and maxes. So meaning you have to be able to plug it. So for C, we've got 2 comma -3. That is an absolute min. There's no lower value that your function will produce for you. Okay. But for D, are there any absolute maximums on this? Well, is there some maximum value that the function will spit out? The answer is no, because this ray shooting up to plus infinity, that means like there is no global maximum. There's always going to be some higher value the function can take on. So there are no absolute maxes on this function. Where's my cursor now? No. For E and F, we now take this graph and we focus in, or we take this function and we focus in only on the window from -1 to 1. So we just pretend everything else doesn't exist and we're only focusing there. Okay, and we're thinking about absolute maxes and mins on that closed interval. Okay, well, in terms of maxes, there's one very clear one. But then for minimums, this is where I have to say something about this being a closed interval. So since these are square brackets, these are closed, this is a closed interval, you can plug in -1 and you can plug in 1. And so you actually do attain the value 0, which for this interval is the minimum. So it's important that you can plug those values in. If you couldn't, you'd have to be a bit more, well, it would kind of change the answer. And so that's why, like, usually with this type of problem, you're given a closed interval. Okay, so maximum 0, 1, and the minimum is obtained at -1 and also at 1. So we have those two coordinates, -1, 0, and 1, 0. And now for G, what happens is we end up extending our window just a little bit, and we see that the answer is going to change. So from -1 to 1, we now extend it to 2, -1 to 2. And so we get even more negative values, or well, we get negative values. So in fact, our minimum becomes this point here. It becomes 2, -3. So this is saying that the absolute min max is something that is going to depend on the window that you're considering. Okay. And that comes into play when we do certain, when we do the calculations that are very typical for this section. So for, and number 9 is is a fairly typical problem. So the idea is you're not given the graph function, but you're given like in symbols what the function is, and you have to find the absolute min and max on some particular window. Okay, and so the process that you do for this, I think it is mentioned in the slides, but I wasn't carefully looking at it. Yeah, okay. So in the slides, you'll find it under the topic of closed interval method. That's what Craig likes to call it. Since you are given a closed interval, it's sort of a method. But the idea is that to find these absolute mins and maxes, the first thing that you kind of know, the first fact that you know, is that these absolute mins and maxes occur only in 2 possible kinds of places. They either occur at the endpoints, which is sort of something that we kind of saw from just playing around with these problems. We saw that they can occur at the endpoints of our interval that we're sort of like cutting the function at. And they can also occur at what are called critical points, which I don't know if he talks about. I think he does talk about it, but it's didn't show up on the homework. But so critical points, which are points where the derivative of the function is equal to 0. So usually when you start this process, you take the derivative, you set equal to 0, and you solve. That will give you what are the critical points, or critical numbers as they're sometimes called. And then you plug in to your original function the critical values as well as the endpoints of your interval. And then you just look at what's the highest output number, and the lowest output number, and those are your absolute maxes. Okay, now let's just run through this process for number 9, and then that'll be it for today. So take the derivative. I'm going to get cosine of theta minus 1. So I then set this guy equal to 0, and I solve. Okay, and so now this ends up being a trig question. When does cosine of theta equal 1? Well, if you think about the unit circle, cosine of theta equals 1 here on the unit circle. So that corresponds to theta equaling 0. Technically, there are more repetitions, right? You can always add a 2 pi to that, or subtract a 2 pi to that. But because of our window in question, this is the only answer, right, for this particular window. Okay, so now we have the critical points. There's only one, theta equals 0. And so we need to now plug in endpoints and critical points. So I'm just going to list them in order. 2. I might need a little bit more space actually, but I'll manage. Okay, and we plug them into the original function g, right? The reason is because we're looking for the actual value. Now what we do is we're trying to compare the values. So that's why we plug into the original function. Okay, well, plugging into this original function, we'll get minus pi over 2. Wait, no. We get minus 1. Sine at minus pi over 2 is around here. That gives me a minus 1. And then I get plus pi over 2. Here I just get 0 minus 0. And here I get 1 minus pi over 2. Okay, so then the thing is you just sort of think about this. And pi over 2 is about 1.57. So this guy is greater than 0. And this guy is less than 0. Okay. And so from that, you can end up concluding that this is an absolute max, and this is an absolute min. I guess technically you should say for that interval, but usually we leave that off, I think. So in this particular situation, the critical point didn't give us anything, but that can vary from problem to problem. And I think one other thing is that like in the slides, he seems to write like it's the absolute max, what am I trying to say? The absolute max, he's treating it more as like the whole point. So the coordinate pair. So like we could just rewrite this as a coordinate pair. -1 plus pi over 2. And this one would be pi over 2, comma 1 minus pi over 2. So yeah, sometimes the problem is phrased like, find what is the absolute min value, max value. In that case, that would just be the y value. That would just be like these two values there. Sometimes it's in terms of like where is it located, in which case you kind of would prefer to see like the coordinate pair listed. All right. Any questions? Well, if not, then we'll end here. And next time we'll do 10 and 11, which are problems that are very similar to this. So it's a good idea to try going through them before for next time.